there must be a head, and no more than one head, only one head so far. And the rest of the components, they can repeat in the body virtually infinity. But of course, we establish a limit because for practical purposes, we use it 100 components as the limit. But the body could just keep on growing forever. So here we have the head, that's the core component, that's where the board, the processing board goes. There we have the brick, which is pretty much a cell, it's an extension of the body. And then we have the touch sensor, and then the motor, that's the actuation of the robot. And all these parts, they can connect to each other with exception of the sensor that cannot be connected to the joint. So the thing is, it's 2D structure, so the head has received connections all around it, also the brick and the joint only in two opposite directions. Okay, so we define the design space. Let's talk about the representation. I'm using an L system, and this L system is encoding the morphology, which is modular, and the controller, which is a neural network. So I'm not gonna. So the L system starts as simple as possible. It starts with the head because that's the rule. So you can only have one head, and then you have a bunch of rules that develop. And we're not going to go through these rules because we don't have a lot of time, but it's pretty much a stage of early development on which you start with the head, and according to these rules, you turn into a more complex string. And it's like an early developed phenotype in a way. So this is the string, and what I'm showing here is the late development. So this early developed phenotype is turning into a body and a brain. So I'm just using a very simple example of robot. So very tiny robot, tiny brain. Here we start with the hand, and then here goes the hand. Can you see the pointer?
No.
That's really sad.
The white space. All this was on like flat.
Is there anything can be done about it? No? Okay. So we have the head, and then we start here with the hand, and then we have one command that adds a block to the front, adds a sensor to the side of the robot, and then we have a new command that adds one block to the front of the robot, and so on. I'm not going to go through the whole string. Here we have a command that adds a joint to the robot, and then we add the joint. Of course, you need a neuron to control this joint, so automatically you get a neuron to the network, and this is an oscillator neuron. And you keep on going until you have both body and brain ready. So this is one example of ready-to-go robot. This is actually examples that we saw on the video. This is the turtle. This is the salamander. This is a top-down view. And then we had to come up with descriptors for these phenotypes. So we come up with 9 measurements, 9 descriptors, and they tell us properties about the body. Of course, they don't tell us all possible properties about the body, but this property seems to be enough. For instance, the number of limbs of the body, the length of these limbs, the symmetry, proportion, and so on. And this is a relative measure. So all of these measures, they go from 0 to 1, and they are relative to the size of the body. Okay, so we have this parameter here, the design space, and then we have a representation that builds over the design space, and then we have a process of decoding this representation into phenotypes, and finally we have descriptors that measure these phenotypes. And all of this is what composes our search space. So our search space it regards the phenotype of the robot. And if you think of that, it kind of creates a multi-dimensional space, so kind of a cube, but we have 9 dimensions. And we break these dimensions into 100 bits to make it feasible and comparable. And this is the granularity with which we analyze the search space. So we talked about morphological descriptors, but we also need behavioral descriptors. We don't have so many, only one. And this descriptor is called speed. And that's the speed of the displacement of the robot from the initial to the final position. So if the robot just plays around, even if, let's say that robot B is faster than A, but it's just going around and doing nothing, that doesn't matter. The fitness will be the same because you have to be going somewhere. Otherwise, just keep moving laterally. So this characterizes the search space. And now let's go to the experiments themselves. So we ran 4 types of experiments using different selection preferences in each one of these experiments. So first one is just novelty search, and it's not behavioral novelty search, it's just morphological novelty search. And it's pretty much the distance, the average Euclidean distance regarding the 9 morphological measurements that we defined. Then the second one is just speed, so it's just behavioral. The second one is a combination of the 2 first ones, so it's speed and morphological diversity. And the third one is also accumulation of the second one, so it's speed, morphological diversity, and a specific reward for a specific trait, which is having multiple limbs. Okay, so let's check the results. So the first thing we have here is the behavior, which is speed, and it's as expected. So speed S1, let's remember that S1, speed 1 is just speed, speed 2 is speed and novelty, speed 3 is speed, novelty, and limbs. And of course, only speed is kind of a greedy search and gets the very best result because it doesn't care about diversity. Second place is speed 2, it's the one that's rewarding novelty or penalizing for the lack of novelty. And after that, we come with S3. So you see that the more you insert constraints, like I want it to be like this, I want it to be like that, the worse your performance goes. And of course, novelty that's purely diversity, morphological diversity, then it performs really poorly, as expected. And if you look at the right there, diversity levels is exactly the exact inversion. As expected, of course, novelty maintains the highest levels of diversity, and speed, that's just behavioral, goes really greedy and loses all this diversity. So nothing here is new so far. That's what we expected. This is good, but oh, nice. Thanks. But the plot here in the middle, this is kind of curious. So we have this measure we call number of sample cubes. So remember before we had this cube, and we are trying to understand what's going on inside this cube when we use different fitness functions. Let's not say fitness functions. Stella is not here, so let's not say fitness. So I can't say fitness function because he's not here. So as expected, also. In accord to the plot at the right, we see that speed has much worse or much fewer cubes sampled. So this is about the exploration of the search space. This means if you have that cube with the 9 dimensions and the 100 blocks in each dimension, let's imagine you have just created a robot and you measure this robot and you set this robot in one of these cubes. And you do this across all the whole process of evolution, and you keep on counting when new robots pop up. So this is showing that how novel, in a way, that your search is. And of course, we see that speed 1 is much worse in doing this than novelty. That's expected. However, we see the blue line and the purple line. This curious effect of getting more exploration of the search space when you combine novelty with speed or with speed and the limbs. Not clear why this happens. We have a third paper that goes into this. Still doesn't explain why does it happen. It happens, but that goes beyond from this talk. So here we have another plot that's about the revisitation. So every time I create a new robot, I try to set this robot inside the cube. And if the cube is empty, I count one more. This is the one up here. But if the cube is not empty, that is, if that morphology has already popped up in the past, then I count it here. So that's the recurrence of the morphology. So the same robots that keep popping up along the evolution again and again and again. And we see that it's not uniform at all. We see kind of a parallel distribution here, and it happens for all of the 4 selection preferences. So it's like a bias in the search space that happens here. And then we wonder, who are those individuals that they're so popular, that keep popping up all the time? And here they are. So here is full evolution. Those are the 10 most popular individuals from the left to the right in 3 sample runs. We're not going to have all the runs here. For each one of the selection preferences. And we see that there, even for novelty, there's this very simple shapes. The main trait there is like having 1 or 2 limbs. And so we see the bias here. And also for speed 1, we also have a bias, and it's a similar bias. It's 1 limb. Pretty much all of them have 1 limb or 1 or 2 limbs. And speed 2, it becomes a little bit smoother. We still have the same bias. This is very confusing. So this is just like this. So. And even in speed 3, that is explicitly rewarding limbs, we managed to see that the dominant morphologies still have 1 limb. This looks a little bit annoying. However, when we look at the level of generation, so we have gone through the whole evolution, and when we look at the very last generation, the best 10 individuals, and then we see the strength of flexion pressure making a difference. So novelty search, okay, they're mixed. No longer we see this bias here, they're really mixed. Speed 1, they all turn into snakes, or just 1 limb, because this seems to be the best strategy for some reason. Speed 2 starts developing more limbs, and speed 3 is full of limbs. So we see here that there is a bias in the search space. Not clear why this happens, maybe a combinatorial issue. But selection pressure is taking care of it, at least in the level of generation. I mean, you get where you want. It could be that this is a cost for you. You don't want this popular shapes to be popping up, so they could be expensive shapes. We don't know. And you can see this more clearly with these plots because they show the averages of these values, of these measurements, along the whole the whole evolution. So for instance, limbs, that's one of the most interesting cases, we see that it goes in 1 direction. For S1, speed 1, just goes down, and for speed 3, it goes up. And for all of the measurements, we see that there are at least 2 fitness or 2 selection preferences that are broken in different directions. So that means that we can influence all of them with the selection preference. Another behavior indicator, this is not numerical, this is something we observe because it's a little bit hard to measure this, but by watching these best robots, the same ones that we saw here, the very same ones, we have specific patterns of locomotion. In the case of novelty, there's no dominant pattern of locomotion, and actually they just move nonsense because the behavior was not taken into consideration, so that's reasonable. And speed, they row, they seem to like to row, as we saw in the video, and that's the strategy that outweighs all the others. Speed 2, they tend to row, and the characterization of rowing is moving. If you have 2 limbs, you move these limbs at the same time. And speed 3 gets where we want because we think walking is cool for some reason, maybe because we walk, and then we push them to have limbs to see if they would walk. And they do walk, indeed. And the characterization of walking is alternating limbs, not moving them at the same time, maybe to keep constant speed. So the first part of the conclusion, the selection pressure does overcome the bias. All of the descriptors can be influenced by it, regardless of bias. There are some preferences, some selection preferences that have a different capacity of exploring the search space. And of course, when we introduce the morphological preferences, the diversity increases, but then we lose in performance. If we think of the walkers, they perform much worse than the snakes. And the second part of the I put it separately because this was not an original question. This just happened to be. When we look at the results and watch the robots, and we talk to biologists, and they presented animal-like morphologies and behavior. This simply emerged. So I think that this tells us something about the potential of the system. Like if our purpose, maybe you can read this last statement, but that's pretty much what I'm going to say. If we are trying to get inspiration from nature to develop a system that is autonomous, and we manage to solve similar tasks as nature does, but not only this, it solves in a similar way, so it tells us something about the potential of the system. I'm not sure if it does validate it, but it tells us about something positive about its potential. So for future work, we want to see what happens if we change, with these morphologies, if we change the environment in different ways. And now we have a baseline to compare what is normal and what's not. And then finally we get to the, let's say, genetic regulation of these robots that would be regulating both body and brain, consequently behavior. Thank you.
Thank you. So, questions? Yes.
Thank you very much, Karin. It was an amazing talk. I really loved it. I was wondering, I mean, I have at least 3 questions, but I'm going to focus on one. So, yeah, let's say, could you come back to the slide 9, please? Yeah, that one. So here you said, okay, we define a set of morphological descriptors, 9 it is, yeah. We chose those ones because they seem to cover more or less what we're looking for. Okay, so that's very, very good. I'm not criticizing that. What I'm saying is that there's been some work, like I guess 4 years ago or something like that, about generic behavioral descriptors. And I was wondering, would you have some idea about maybe developing some generic morphological descriptors? Something like, for example, taking a video and extracting some features and in an automatic way.
Yeah, as I said, to classify the behavior we had to watch, and to classify on numeric is just to get an insight. And I think behavior maybe would be too much beyond the time we have to do this. So what's going on right now for me is coming up with measures for the controllers. So not only the body, but also the brain will be measured. But the behavior that emerges or results from the body, brain, and environment, and then it would be more difficult. Like it would go beyond. If I had time, I definitely would. As you said, get the patterns of the images and try to understand. But I think that's a PhD for somebody else, probably.
Well, that's something I've been interested in for a long time, but never had the time to do it. So if at some point you want to collaborate, I would be happy.
Absolutely.
Hi, Boris here. This classification of animal-like behaviors remind me of our work with 2-dimensional soft robots, in which we also seen emergence of various animal-like behaviors without actually looking for novelty. That was just looking on fitness. So we may discuss that afterward. But my question is, you mentioned that when you include novelty in your measures, in your selection, then you don't necessarily find optimized for speed. Have you investigated what would happen when you switched to just rewarding speed after first evolving for anything that included novelty, and whether that would allow any of the parts
switch to what?
To just speed. So after running, for example, for speed, limbs, and novelty, then you switched your selection just to speed, and whether any particular lineage that then has limbs or has rowing or whatever could be optimized further without degrading, so as to speak, to snakes.
No, I have not. I read some work of other people who have done this, and they conclude that it didn't help anything. I don't remember who. But however, they were doing behavioral novelty, and I'm doing morphological novelty. So it could be. It's something that we try and do. Thank you.
So can the next speaker start installing? And there is time, like there are a few seconds for one last quick question. Well, actually, I have a question that's not quick though, so I'll try to make it quick. So when I look at your morphological descriptors and what you're doing with beads and novelty, it's kind of, in looking at the cube, it kind of reminds me of an algorithm called Map Elite. So have you considered using that approach as well to try to look at the landscape of all possible morphologies that you get?
No, I have not. I think it's not the first person who tells me this, so yeah, I should look into that as well.
All right. So thank you.
Thank you.
Okay, so the next speaker is Ayaan Zahada, and she's going to talk about locomotion as a result of displacement of resources.
Hello. The title of this talk is Locomotion as a Result of Displacement of Resources. But actually, even there is locomotion in the title, you will see quite a bit about plants. And plants are not supposed to locomote as we know them, except maybe this kind of plants, which... but don't worry, I'm not going to talk about these scary walking plants. I'm actually not talking about any kind of walking plants. The reason that we have plants and locomotion here is that I will talk about an algorithm which is inspired by plants. So the algorithm was initially developed for a different reason. So it was developed for growing adaptive structures. So structures that grow over time and stay adaptive to their environment and changes around them. And the algorithm is inspired from the growth and morphogenesis of plants and based on the distribution of limited resources, which leads to this growth. And here, with a small change in the algorithm, we achieve an amoeboid-like, at least it looks like amoeboid locomotion. So the algorithm was introduced in the context of an EU-funded project, Flora Robotica, which deals with plants and robotic structures living together as a biohybrid, and they're supposed to grow into artifacts with architectural properties. And they need to be adaptive to the humans around them, the design requirements.